Thank you, everyone. Welcome back. As you can see, we have Paul Davies, Lawrence Krauss and Rachel Webster with us for a discussion of all the things that we've heard about, a way to find out what we still need to know about the universe, how we can probe these issues further. Before we get started, I just want to introduce Rachel Webster to you. She's had a stellar career teaching and researching astronomy. She's currently at the University of Melbourne, where she's the chair of the academic board and leads the astrophysics program in the Department of Physics. She did study for her PhD at Cambridge University. Her research is a combination of observational and theoretical work, and some of the areas of interest are the epoch of reionisation, which of course she will be able to explain to you exactly what that means, and the period of and how galaxies form. She's been a key collaborator with the group building a new low-frequency telescope, the Murchison Wide Field Array in Western Australia, that will enable us to get more information about the first sources of the universe. And she's a principal investigator with the ARC Centre for Excellence for All-Sky Astrophysics, which is a huge and significant research project. So please welcome Rachel Webster. I'm going to start by asking all of our panellists to answer a question, but then we're going to find out a little bit more from Rachel about her work. And then we'll have time to explore some of the issues that Paul and Lawrence have raised and time to take some questions from you. There are microphones in the audience, so when we do cut to question time, lights will come up and we'll be asking people to walk to one of the microphones, one on each side downstairs and one on each side upstairs. So be ready. Now, one of the things that became really clear in the discussion, in the talks from Lawrence and Paul, is how fascinating these questions are because of the science involved, but also because of some of the other aspects of what it means to ask and try and answer these enormous questions that have philosophical as well as scientific ramifications. And I want to ask each of our speakers an origin question, really, which is how did they get interested in this area of science? How did they come to be working in this area? Now, we might start with Paul because he has told us a little bit about that person in the 1960s who was fascinated by the idea of aliens. So we might start there and get you to tell us what triggered your interest in this area and how did you become to be doing this kind of research?
Well, specifically on the origin of life, Schrödinger, the physicist, wrote a famous book called What is Life in 1944. And I read that book when I was a postdoc in Cambridge, and up until then I'd never really thought of life as somehow very special. I mean, obviously we recognize that living matter has weird properties, but he really brought out the fact that to a physicist it looks like magic. And so ever since then I've been fascinated. I think I can trace it back to Schrödinger.
And how did you end up in physics?
Oh, I was a physicist anyway, so I started out in physics, because why would you do anything else? Lawrence probably heard this one before. I divide the world into physicists and the rest. And there's only one decision young people need to make, and that is, do I do physics or something else? And if it's something else, it really doesn't matter what you do. So you see, I'm a physics chauvinist. So I was born a physicist, and I knew I was going to do that from the age of about 12 when I was messing around with photography and making telescopes and all that sort of thing. For me, it was a fast track, as you can do in the British education system. After the age of 16, I studied only physics and mathematics. Wow. And that was it. So I knew where I was going to go. And so by the time I was a postdoc, I sort of felt I was on top of physics, so, well, let me have a look at biology. So that was it, really.
I'm thinking about anybody who's 12 and making those kind of decisions. Was there someone in your family, was there somebody that you knew? No, it was completely abstract.
No, they all thought, this weird son. My parents had no idea what I was doing. And I have to say, no real interest. And I was the first, and until my brother went to university, the only member of even the extended family who'd gone to university. And it was all just a great mystery. And as far as my mother used to say, she was a bit upset I was going to be a scientist, but she said, well, if you've got to be a scientist, two things she said. One is, can't you go and work for a big company that will give you a good pension? And the second thing was, can't you build a robot that could help me do the housework? So I'm still I failed on the former, I'm still working on the latter.
Lawrence?
You want me to do the same order?
Yeah. Well, no.
Okay.
However you want to tell it.
Let's see. I'll start at the beginning then. Long time ago. No. I got interested in science. It's hard to know all the reasons. Again, I was actually neither of my parents had finished high school. But my mother wanted me to be a doctor, my brother to be a lawyer. And unfortunately, my brother became a lawyer. And professor of law, which is even worse because that makes lawyers. But my mother convinced me that being a doctor, I think to get me interested in medicine, convinced me that doctors were scientists. So I got interested in science because I wanted to be a doctor. And then it was only when I was in high school that I discovered that doctors weren't scientists. And a great disappointment to my mother for a very, very long time. So I think that definitely played a role. But also, more importantly, I think when I was younger, again about the age of 11 or 12, I was reading books about scientists and by scientists. I remember reading a book about Galileo when I was 10 or 11, and then which had a big impact. And then reading books by scientists, George Gamow, Albert Einstein, Richard Feynman, all those people. And so that's, by the way, one of the reasons why I write books, is sort of return the favor, because that really got me interested. And I think it was actually Feynman when I was late high school, when I was on some program and some teacher realized I was a little bored and gave me a book by Feynman to read. And it was the first time that I realized that, first of all, that there were open questions. I mean, I'd been fascinated by the science that had been done, but when I realized there were lots of things left to do. And then, interestingly, though, while I've been a professor of astronomy as well as physics for many, many years, I never took an astronomy course in my life. I had a telescope, but usually it was to look in the bedrooms of people who were in the neighborhood. But very little stellar astronomy. But when I was trained as a particle physicist, and it was only sometime when I was a postdoc, I guess. No, when I was a graduate student, that I began to realize that the universe could be a great place to probe fundamental physics. So that's what's always driven my interest. But for the students out there, I think the one lesson, if there's anything from this rambling talk, it's that most of what I know about cosmology and astrophysics I learned after my PhD. And I think that's really important for students to realize is that much of what you learn is after your degree, and it's a lifelong learning process. So that's really, I think, the important lesson I want to say.
Rachel?
Well, unfortunately, I'm also a physics tragic, and it started very early.
I would expect nothing less from the people on the stage today.
I think it was when I was in grade 3, we were asked to do a project, and we had a fabulous teacher who was an environmental scientist, and people were doing butterflies and native flowers and all of those sort of things. And I remember the teacher said, and you could even do a project on math if you wanted to. And so I thought, great, I'll do one on maths. And I was sort of so impressed by this running against the crowd that I asked my mother at the time what I had to do in year 12 to continue in this line. And she said, well, you do pure and applied and physics and chemistry and English. And that's exactly what I did. But there was actually another really important event, which was when I was in year 12, the University of Sydney runs a school for high school students, some international students, some Australian students. And I managed to get myself invited to this school, and it was on inner and outer space the year I went. Mm-hmm. And we had Alan Shepard, which was fantastic. We talked about why women hadn't been recruited to go into space at that stage. But there was a lecturer who talked to us about cosmology, and that just blew me away at the time. You know, I was about 17. And I remember many years later when I was on the faculty at Melbourne, I was suddenly thinking, who was it who gave those lectures on cosmology? Because I know nobody at the University of Sydney capable of doing that. And I went and looked at the book.
Sniping in our hometown.
No. That was many years ago. Many years ago. So I went and looked up the book, and the name was Robert May. And at the time I thought, Robert May? And indeed, he left the University of Sydney, became a professor of evolutionary biology,
sure.
And so physics into biology.
President of the Royal Society.
President of the Royal Society. He's a phenomenal lecturer in cosmology as well.
Excellent. Huh.
So there.
And it's wonderful, I think, to go back and remember those particular stories too. Rachel, can you tell us a little bit about your particular areas of research and what you're working on, and to give us a little bit of context of what's happening here and now in these areas?
All right. What I'd like to do is just describe a project that we're doing out in Western Australia, and we might show the video of the telescope that we've built out about 350 kilometres northeast of Geraldton. And this radio telescope, if we can have the video come up, is very unusual. It's unlike the Parkes radio telescope that you saw a little bit earlier. And what you'll see are tiles on the ground. There's 128 of these tiles laid out in the desert, no moving parts. And the reason that this is such an unusual telescope is that we're trying to measure light, radio light, that has a wavelength of about 2 metres. And it's a signal from the neutral hydrogen atom, and it's emitted right back in an early part of the universe. Not quite as early as the time that Lawrence was talking about, but after that cosmic microwave background is emitted when the universe is very smooth. After that time, the universe is filled with neutral hydrogen, and there's very little structure. And that's, of course, not what the universe looks like today. Today, we've got lots of stars and galaxies, and very little neutral hydrogen between those galaxies. And so we know that sometime in that period between when the cosmic microwave background light was emitted and today, that the first stars had to turn on in the universe. And so what we're trying to do is we're trying to find that time and to characterise the birth of those first stars. And the signal we'll see will be holes in that neutral hydrogen where the ultraviolet light from the stars has reionised the hydrogen, so it's broken that hydrogen atom apart again, and so the structure becomes, it's got holes in it. And ideally, we'd love to image those holes, but we won't be able to do that till we build the square kilometre array, which may happen in about approximately a decade's time. But we can actually see the statistical signal in that neutral hydrogen. But the really interesting part about this is that the hardware, as you saw in the little video, is actually very simple. It's just a bit of chicken wire, as we sometimes say, with a few little dipoles laid out. But we've collected over 5 petabytes of data from this telescope. This is an extraordinary amount of data. It's, there's probably not many projects in the world that would have this scale of data. And so really, the telescope isn't the problem, it's the software to take that data and then to find buried under many orders of magnitude of what we call rubbish, but is really the signals from our galaxy and other cosmic objects. We're trying to find those little signals from those very first stars. Enormous software problem.
And I'm happy to say that one of our colleagues at ASU was a collaborator on your...
We've got one of those little gadgets down our corridor.
Yeah, exactly. Yeah.
And that video, by the way, in case you're wondering, was taken by a drone, science's friend.
Was it real, though, or was it a digitally enhanced?
No. That's the real thing.
I've seen the drone too.
Yeah. So tell us about the square kilometre array. I mean, because these things are challenging whatever we thought, those of us who are lay people. I did joke earlier on to some of our panellists that my physics career finished, apart from studying it for the HSC, but it finished at age 10 when I stopped being my physicist father's unpaid research assistant, as soon as another child was sufficiently skilled to do the job. Tell us what the square kilometre array would enable, what that project is and why it's important.
So it's basically a project to greatly expand the amount of collecting area that we have for, I would say, a radio telescope. But in fact, it's become it's an international collaboration, which means that, of course, it's got a lot more complicated as it's gone on, and there are at least 2 radio telescopes now involved, and possibly a third, and so they're optimised for different wavelengths. So there'll be one in South Africa that will look at what we call mid-frequency, which is about 1 to about 5 gigahertz, which is the traditional radio frequency wavelengths. The one that I'm involved with is these long radio wavelengths, and that will be built in Western Australia on the site that CSIRO has developed in the Murchison. And it's a phenomenal site, absolutely brilliant infrastructure, and the project that I'm talking about is really the core project that we hope to do with that telescope.
So this is something for people, potential students of in these areas to think about for the future work in Australia. Did you want to show Did you want to have a look at those?
No,
we'll go on. So the work that you're doing is really about a particular period in. What are the other kinds of, if we look at that kind of history that we're talking about from the time that you were talking about a billionth of a billionth of a billionth of a second, this period of galaxies, what are the other pieces of that puzzle if we look at the kind of building up that picture of the history of the universe?
Maybe, well, do you want to, well, there's a few points. Let me, by the way, just say, and I'm not biased here, this is that after the first second, the rest of the history of the universe is boring. But
I'm seeing the
no. But let me say something that's interesting that I think is fascinating, because we think in logarithmic terms, in at least in cosmology, and it is interesting that there were more interactions, particle interactions in the universe in the first second than there will be in the rest of the history of the universe. It's kind of interesting if you work out the numbers. It's fascinating. And of course, it's not true that the rest of the history of the universe is that interesting, but it's really amazing to think about how much stuff we need to know about that first second. But the other area between the first second and the microwave background and the time that Rachel's talking about, I guess one of the it may be before reionization or not, is that we're trying to, or maybe after, so there's when stars formed, and then there's when galaxies formed, and large black holes, and the key open question of which formed first, the black holes or the galaxies, and that's what the James Webb Space Telescope, I think, is being built for. That's another big epic. And then, of course, I guess the next epic would be when life began. We're probably, if it isn't difficult, then we're probably not the first version of it. But
absolutely,
yeah.
Because the solar system's only about a third as old as the universe.
Although the question, on the other hand, as I pointed out, the heavy elements required a bunch of generations of stars, so you probably couldn't have done it early on.
But the big early stars were churning out carbon pretty fast.
Yeah, so you probably
I think you could have had life 8 billion years ago,
8
no
billion,
problem.
I'd say, yeah. Any other epics you think about?
No, I do think this period, which between the cosmic microwave background and basically as far back as we can see with Hubble at the moment, which we usually call the Dark Ages at the moment, because there's a lot goes on there, and even though it tends to be an observational domain, which is probably why you...
No, I think it's all observation. If we just left it to theorists who would know anything. I'm absolutely I'm a theorist, but the universe surprises us. We can't do physics, or we can't do science.
It always takes us in interesting directions.
Yeah, it surprises us. It's really important, and that's why it's worth. I mean, when people like Rachel build telescopes of that sort, it's really important to realize that, especially to convince funders, you have to tell them what you're going to do, but you're never really sure. And what you really hope is that what you'll see is nothing that you expected.
Exactly.
And it happens a lot.
One of the things that we want to talk about a little bit in this discussion are the things that we need to find out. The questions that we need to find out next to take all of these areas of research to the next level. Now, that's a huge amount to discuss. But before we move on to that, one of the things that came out of Paul and Lawrence's talks were parallel observations about the laws of nature, I guess. Lawrence, you were saying, what if the laws of nature what if it's an accident? What if the universe is an accident, and how disappointing that would be to you in some ways? Paul was saying, what if posing the question, is life a fluke or is it a cosmic imperative? And I just want you to talk a little bit, Lawrence, about why it would be disappointing.
Well, I mean, the fact the universe is an accident isn't disappointing, because it most certainly was. Namely, there was no planning. But I guess it's only a matter of training. It's like it's a generational thing. And was it Max Planck said, physics precedes a funeral by funeral. And and so I'm still around. But I was trained, and I think Paul was, and to try and think about how we could understand why the universe had to be the way it was. Is there a unique fundamental structure that if you changed anything, the whole thing would fall apart? And that was a goal. And then if you learn that, as at least the evidence suggests, that all possibilities may exist, that there may be nothing special about the specific conditions of our universe, that's a little disappointing, because you really want to explain why the universe has to be the way it is, rather than why it's most likely most universes are quite different. And also, but the other thing that's disappointing about it is, and Paul really framed the question well in terms of life too, unless you know the set of possible possibilities, you can't do what's called a measure. You can't do reasonable probabilities. So he's right. Whenever people say that, there's this likely that life exists, it's just a number that people pick out of there. Well, if we don't know all of the set of possibilities, then it'd be very difficult for us to say how likely a universe is like our own. And so when people talk about that, and you'll read about it, it's the same kind of garbage that Paul talked about when you read about...
people have tried to put a measure on the space of the multiverse or the law, different universes, and it's hopeless.
It's hopeless. It's probably less. Yeah. It's probably more hopeless than even life in some sense, because we don't know what the locus of possibilities are. It's hard enough. We haven't even figured out the details of the laws that govern our universe to know all possible laws. But that's why I spent part of my talk on the gravitational wave stuff, because that I find very exciting, because that might at least allow us an empirical handle, because as we agreed, unless you can observe it, it's just talk. Yeah.
And I think there were probably some of us in the audience who were slightly disappointed ourselves that, that beautiful image you showed us didn't turn out to be,
and I want to point that out. I didn't have enough time to give it justice. It isn't necessarily wrong. It's just not right. There's a huge difference. And in some fields of science, like medicine, it would be right. Yeah. Namely, what we've been able to show is that it's only got a likelihood of 92% of being right, which is enough for us to say it's not right. Because we require in physics 99.999%. So the 8% of the universes that you would measure, it would just be a random bit of noise. And so I think the reason people keep talking about it being wrong is that so much press that was given around the announcement that it was such a big disappointment. But it still may be there, and it still may be. But what we've learned, and this is really unfortunate, and Rachel talked about the garbage in the telescope she's looking at that gets in the way. We were very, very fortunate in the cosmic microwave background that we were able to get rid of the galaxy. I think many of us, before it was done, I don't know if you felt this way, but I thought there's no way they'll ever see a signal. The galaxy will just get in the way. And then it turned out it didn't. And I think people started to say, oh, well, it's always that way. But it may just be that when it comes to looking for this signal, the galaxy will get in the way. And as long as we're stuck in our galaxy, which is quite a while, we're not going to be able to look for it.
Paul, did you want to add anything to that, the question about fluke coincidence versus cosmic imperative in relation to what you were talking about life?
People often say that if life is just a product of ordinary chemistry, well, then that's going on all the time and shouldn't it inevitably follow. It's very easy to cook up a scenario in which you can see that this simple reasoning doesn't work. So imagine, and this would be grossly simplifying, that the origin of life required 10 chemical steps, and that the first step had to be in a temperature range from 0 to 5 degrees, and the next one from 25 to 30 degrees, and so on like that. And then maybe for 1 hour, and then 3 hours, and you can put whatever numbers in. These things exponentiate, and so you can say, how likely is it that you'd have a sequence of those windows in the same place, on the same planet? And it's very easy to convince yourself that the odds could easily be less than the total number of planets in the observable universe. So it's not hard to think that it could be very, very unlikely. And that would be depressing, I think, but it would give us a special significance if we convince ourselves we were alone in the universe, the only planet with life. We'd better look after it a bit better.
Can we talk a little bit in terms of going to that idea about what are the next things that we need to find out? Can we talk a little bit about, I thought that it's incredibly interesting for those of us who don't think about these things every day, to think about that idea of more than one occurrence of events that lead to life, that there might be life one, life two, life infinity.
Right. So
what is the research? What are people looking at to kind of test those
Well, I
ideas?
wish I could say that after publishing this stuff a few years ago, biologists dropped everything and went searching for the shadow biosphere. They didn't do that because they're funded to do other stuff. So whenever I get a chance to talk to people who go out in the field and look for new types of microbes, new extremophiles and so on, I say, if you have any that behave in the lab, they won't cooperate with your techniques, don't throw them away, because it could be that they're the very ones that you're interested in. So, for example, I'll give you a very simple example of how life could be different. All known life is based on left-handed amino acids and right-handed neutrinos, but the laws of physics, at least at this level, don't care, left from right. So you could do life the other way around. You could have mirror life. Would we detect it? Chances are it would be all around us. We might have seen it, but we wouldn't notice it because it doesn't like the stuff we eat. So one possibility is to look for mirror life. And that is one little experiment that was done as a result
Although
of...
there's problems with that because you can change left-handed to right-handed. Life can do that.
Life is good at changing left-handed amino acids to right-handed amino acids. It's harder with sugars, but it turns out that there are organisms...
So what was that experiment? How did somebody...
it was actually my wife's idea, Pauline suggested, because she was doing an interview for Radio National, actually, about work in the Atacama Desert, where there are Mars-like soils. And so it's a great place to go if you want to see, could there be life on Mars, how would it get on? You go to the Atacama Desert and you see what can live and so on. And so I should back up and say that a lot of people think that NASA has spent many, many years looking for life on Mars. And every time they fly a mission to Mars, it's always, there's one reason they're going to look for life. Yeah. Don't believe a word of it.
Yeah.
The last and only time NASA looked for life on Mars was in 1976, the 2 Viking landers. And one of the experiments that was done there was positive. It was by Gil Levin, who is actually an adjunct professor in the Beyond Center at ASU. And he basically had a nutrient medium that he poured onto the Mars dirt and to see if it would fizz, and it did fizz in both places, and then he heated the sample and it stopped fizzing, exactly as you would expect if there was life there. But other scientists said, it couldn't possibly be right, there must be some other explanation that they've never completely explained, but presumably some weird soil chemistry. So how would you discriminate between chemistry and biology? Well, what he originally wanted to do was give them left-handed food and right-handed food, and if it fizzed with one and not the other, it was life, and if it fizzed with both, it was chemistry. And NASA said, we can't afford 2 experiments, they took it off. And so it's unresolved to this day. One of these intriguing things in the history of science. He thinks he found life on Mars. Few other people agree with that. But at least NASA have a field station in the Atacama where they tried this. They tried left-right fizzing experiments, and in the inner core of the Atacama, where it's really, really almost nothing living, but it's highly oxidizing soils, they're getting equal fizz, but as they move away from the dry inner core to where there's a bit more moisture and you get more organisms, it fizzes more with the left-handed amino acids and right-handed sugars. So it's a proof of principle, but nobody's going to pay for another biology experiment on Mars. NASA always takes them off. Proposals go in, they're always taken off.
And one of the original ones also probably could have killed life because of perchlorates. It was, people thought, they didn't realize at the time, and so they could have actually destroyed the life they're looking for.
And that's a new twist on, since we know about the perchlorates on Mars, a new twist on those experiments that Gil Levin got. So I think even if it turns out he didn't discover life on Mars, I think he's a bit of an unsung hero. He's been sidelined in this discussion.
I just want to say one thing, because I want to make it public, because I want to win some money from Paul. But No, we've talked about this a lot, but I'm, we've run meetings in Origins Institute on origins of life, and I've listened to chemists and biologists, but I'm becoming more convinced in my own mind that there's a unique pathway to life, and that life is determined by chemistry. And so I have this bet, which I'd love to be wrong about, but that if we ever discover life anywhere else, it's going to have the same chemistry as ours. So, which in our solar system will be very bad because we won't know if it's been polluted by us because of the reasons that Paul said. Parts of Mars are found here on Earth and vice versa, so life pollutes anywhere else in the solar system. But it'd be interesting for me to see, but I would be amazed if, I think that chemistry has driven life, and even the amino acids and even the base pairs of DNA. So I'd love to be wrong. But
I have to say, that seems to me a bit theistic.
Well, no, the way where it's not theistic, Paul, is that I'd love to be wrong.
Life is built into the laws of physics and chemistry. It seems to me
Well, we haven't
to
asked
be
him
too
to
much
unpick it.
preordained.
Well, it's like, you take a ball and it rolls downhill. That's not
Yeah,
theistic.
but to have something like life with all its special properties
It's
built
just a
into
big
that.
hill.
But it's true if there's some anthropic selection in the multiverse. That might be the case. Yeah.
Rachel, what is the question that you would most like to see answered in terms of the area that you work in? What would be something really exciting for that work? And how far away is that? Is it?
Well, I think there are two questions that are really incredibly obvious. One is, what's dark matter, and the other is what's dark energy. The dark matter question, I think we're probably getting quite close to, and we, in fact, have some sensible constraints on. The dark energy question, I think, is wide open. Really, the experiment that got Brian Schmidt a Nobel Prize it's a discovery with almost no theoretical underpinning that I've ever understood to be sensible. So I think we're a long way off there.
I proposed some of the nonsensible ones.
Oh, did you?
No, even I would say that. But
last I heard, there are about 150 different proposals.
We don't have any. We don't. There's no. And unfortunately, it's an area where we really are going to suffer because I think it's highly. While we've discovered it from astronomy, I think it's extremely unlikely we'll learn anything else from measurements except that it exists and has the properties that make it maximally ununderstandable. We need a good idea, and that takes a lot longer. So I don't think there's going to be observational.
No, I mean, I think, and possibly on dark matter as well, but coming as a physicist, I think if we start to understand these things, we may understand a little bit more about why life came into being. I think one of the huge gaps in the theory of everything, which physicists are quite happy to think about, is that life isn't in there. And so they try and explain the physical universe without life, whereas I guess my proclivity would be to put life in there and to ask, well, what does this mean for what we have to understand about the way our physical universe is put together? So I guess I'm on the physicist side that says I think life may be inevitable. It's complex, there's no question about it, but somehow in terms of how we understand the physical universe, we have to understand it with life in there.
In some sense, when we talk about anthropics, and I'm not a big fan of talking about it, we do put life in because we say it's a selection effect.
Absolutely.
That it may be that the laws are there are because first you have to acquire a universe where people can observe it and make that measurement, and that may restrict the space of but I want to defend the fact that many of us physicists don't like the words theory of everything.
No.
Everything
doesn't mean everything.
Yeah, in fact, as a friend of mine said, it's really important. Even if we did have the theory of everything, the type of theory people are talking about, a quantum theory of gravity, it would be a theory of almost nothing. Because it would really help us explain the earliest moments of the Big Bang, but to understand everything else, it's irrelevant, because we haven't needed it to understand everything else we understand.
Right.
So what would you call it?
The Holy Grail. I don't think it's worth calling it because we don't have it. There's no likelihood we're going to have it. And
I see it as the completion of the reductionist program began in ancient Greece. Looking for the fundamental building blocks and cataloging them and understanding their interactions. And that's a project that is completable. we've
It may be
broken matter.
completable. It's not clear. Feynman may have been right. There might have been like an onion with an infinite number of layers. There may be no end to it.
We could believe that we're like 95% of the way, and we might one day say, right, that's wrapped up.
Yeah, it may happen.
We've done that, but then you go in the other direction, in the direction of complexity, and it's going to not help at all.
It's not going to help you figure out how oatmeal boils, or
or political science.
Yeah, exactly.
So, Lawrence, what is something that you would like to see answered?
Well, I mean, Rachel already hit. For me, dark energy, as I say, I sort of proposed it existed a long time ago, but it's totally it's a mystery in deep ways that we can't even describe on stage. It's inexplicable in a fundamental theoretical way, and therefore very exciting because it means hope. But I really am not optimistic that we're going to have any idea of it because I don't think there's going to be any observational guide, and we need to be guided by observation. What I'm excited about are two things. One is the possibility of knowing if our universe is unique by maybe being able to measure the first moments. 5 or 10 years ago, even when I wrote the universe from nothing, it was speculative discussion, but the idea that we might actually be able to get an empirical handle on that is amazing. And the other is the Large Hadron Collider. I mean, I think we've been waiting for almost 2 generations for this machine that may tell us the next, whether we've been like people in one of these isolation tanks. If you're in an isolation tank, you begin to hallucinate. Okay, and theorists have been like that for 50 years because we were waiting for a machine that could give us data. And in the meantime, almost all the papers are hallucinations. Most of them are probably wrong, and most of them are wrong. It's the way it is in science. And so we need some guidance to tell us what direction. And we've got a lot of amazing ideas, most of which are wrong. And so I'm really hoping the Large Hadron Collider it's not going to tell us everything, but it might point us in the right direction.
We've got time to take some questions from the audience. So can we maybe have the lights up a little bit? And if you have something that you would like to ask any member of our panel, do come to one of the microphones. They're still here. I will just ask one question that has come in electronically while we're waiting for that, which is, I think it's a question to Lawrence and Paul, but I'm sure Rachel would have a view on this as well, about biocentrism. So let me just find. What are your views on biocentrism, which is somebody called Robert Lanza, a doctor?
Uh-huh.
So,
we needn't go further.
Whether that biology is the central science in the universe, that life and biology are central to being, reality, and the cosmos.
Well, that sounds like gobbledygook to me. It sounds like New Age.
Well, but Rachel already said she was in favour of this.
Not essential. Did you say? Well, you thought of including it, but did you think it was?
No, including.
I'm not sure we want any isms, but.
Yeah.
But the question, but for me, I think it's a good question, and I'm not sure the answer. Is life a fundamental phenomenon,
yes,
or is it just some weirdo state of matter that just happens in one place? And I think Lawrence was saying, is fundamental to the workings of the cosmos. And I'd love to believe that. I'm still agnostic on this.
Well, I don't know why I'd put it the other way around. I'd say the workings of the cosmos inevitably lead there, but it's
right.
But they also inevitably lead to other things.
But it's a fundamental
They inevitably lead to snowflakes too, and they're interesting, but it's not something sacred, I guess.
Right. It only gets into that territory when we're dealing with consciousness observation, and what for me is more important than the fact we observe the universe is that we understand it, at least in part, through science and mathematics. That's what I find the most awe-inspiring thing.
Well, yeah, me too. I think, but also the fact that we both in our physics work, I think, dealt with this a little bit, we really don't, I think it's still hard to understand, when we talk about science, we talk about systems that you measure from the outside. And so to still understand how to do the proper physics of a universe when you're part of the universe is I don't think is a resolved question fundamentally when it comes to understand the quantum mechanics of a whole universe when you're actually a part of it, and therefore your observations are integrally tied into the nature of the universe.
There's another deep issue, which is what is it about the logical structure of the universe that permits a subset of it to somehow comprehend, image, form a approximation of the totality. Not any old universe would do that. There's something very special about the way the universe is put together that permits that. And that's an aspect of the whole multiverse thing often gets overlooked because that tends to focus on the low energy effective laws of physics, not on the logical structure. But not every universe would have what David Wolpert at Santa Fe calls inference machines. They can infer things about the totality using the same laws as the totality. It's a sort of subtle point, but I think a very important one.
We'll take a question from microphone 1 over here, please. Sorry, it's hard to see.
Hi. We hear occasionally about search for life in media and popular culture, and it usually involves a search for water. And it always makes me curious, is there any particular reason why we assume that if there is life out there, it would work like us and look like us? Is there anything special about carbon and oxygen? Could not there be life from, say, silicon and helium just as easily?
You want to start?
Well, yes, yeah. Well, we have to believe in silicon-based life because it made it into Star Trek. So we've got to take it seriously.
I knew we'd get there sooner or later.
It may become the dominant form of life on Earth, intelligent life on Earth in the future, too.
No, carbon is a bit special. But the other elements, we've got carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Some of the others, I think, are up for grabs, but I think probably not carbon. Water, that's a bone of contention. So there's one very distinguished chemist, Steve Benner, who wants to make a case for a substance that I can never pronounce properly. It's something like formamide or anyway, some other thing, some other fluid. Water is very good at dissolving stuff, and so mostly NASA had this mantra, follow the water. A lot of people made the mistake of thinking that's all you need. They confuse the necessary with a sufficient condition. Find a planet with water on it, hey presto, there'll be life. Water may be a necessary precondition for life, but it's certainly by no means sufficient. But usually, my feeling is when you're searching for life elsewhere, we really don't know what we're looking for. It makes sense to at least start out by looking for life as we know it and understand it, and that does mean carbon-based, water-based life. Let's start there at least.
There's a line that scientists use, which is, if you're drunk and you come out of a bar, and I'm sure no one here has been in that situation, and you lose your keys, you look under the lamppost. Why? Not because it's likely there, but that's the only place where you could find it. So that's what scientists do. They look under the lamppost. The simple thing is to look for what you know. We know at least one form of life, and therefore look for that. And then when you haven't seen that, then you can look for more exotic forms. But there's another thing that's interesting about water, and in the School of Space Exploration, where a lot of people are looking planetary science and extrasolar planets. When people say habitable planets, as Paul so clearly pointed out, it doesn't mean they're inhabited. In particular, a world in which water is accessible may not have life at all. In fact, if there was more water than Earth, if the Earth had just oceans, then in fact it's quite possible that life wouldn't have formed if it was just oceans. And so you could have too much water. So water worlds, while they're a natural thing to look for, does not in any way mean life. And there are other things too. We would say look for oxygen because, I think you said the stromatolites produce the oxygen we're breathing, and free oxygen didn't exist on Earth when the Earth first arose. And so if you saw free oxygen, it's a sign of life. I used to think that, and I wrote it in one of my books. But in fact, there are other ways to create free oxygen. So it's going to be you have to be highly skeptical when you read the next claimed discovery of life elsewhere in the universe. It's probably wrong.
From microphone 2.
I have a question for our speakers. It's a bit off topic, but could I get your thoughts on simulation theory and if the world is a program, just like DNA is a program in a way?
I don't want to hog all the answers, but it's... so Nick Bostrom at Oxford University, a philosopher, has long championed the idea that we're living in a computer simulation. Yeah. And the argument goes something like this. The way I like to express it is that imagine that we wanted to make another universe. We'd need a very big budget to make the real thing. but a much smaller budget, you could make a fake universe. So if we could simulate consciousness, and AI people think they're getting close to that, simulate consciousness, you could simulate a world for these conscious beings, and it would be much, much cheaper than making the real world. And so the reasoning goes that any civilization that is sufficiently advanced that it can make fake worlds, the fake worlds would, just for economic reasons, rapidly out-proliferate the real worlds, and therefore any arbitrary observer is likely to find themselves living in a fake world, not a real world. So that's the essence of the simulation argument. It's very compelling, but if you believe in the multiverse, you've got to have all the fake worlds in as well as all the real ones in that mix. You've got to put a measure on the fake worlds too.
But then, well, yeah, I think it's typical of a philosopher, but it's really, I think it...
So we've dealt with lawyers, doctors, philosophers.
Well, yeah, I'll keep going until I offend everyone in the audience. But first of all, I think it's if the simulation is sufficiently good to be indistinguishable from reality, it doesn't matter. The question is unimportant. We want to learn the laws that govern our universe, and they're real laws to us because we experience them. So I mean, it's an interesting question that I don't think is relevant to operational issues. I also think if it were a simulation, it'd be done better. But the problem with that argument is it's the same as the problem with the God argument. Because you're assuming there's a life form that creates a simulation. Well, how did that life form get there? Was it a simulation? And was there another simulation as it turtles all the way down?
It has to be a simulating system.
Yeah.
And the other weird thing that you get when you, because I love this stuff, is that, the essence of a Turing machine is it can simulate another Turing machine. So a Mac can simulate a PC, sorry to mention.
A lot easier than a PC simulating a Mac, because one is much higher on the evolutionary scale.
So the point is, if you have a Turing machine that makes a world, then there are aspects of that world that can simulate their own worlds and their own worlds. So kind of universes, creatures and creators in a nested hierarchy. And then I've got a slide somewhere I occasionally show when talking about this. Will the real universe please stand up? Because it's just so it's a sort of reductio ad absurdum, I think, of the whole idea.
Well, it's the problem of infinities. Whenever you have an infinite number of possibilities, you can't do... It's hard to do science. It's hard to do probabilities. Once you have an infinite space, unless you know the probability measure, then you can say, you can produce logical contradictions with infinities in almost every way.
It's the Tower of Turtles problem.
Can we, just having touched on philosophy, the interesting thing about our discussion today is how much of this science and the kind of, particularly also the kind of writing that you have both done for popular audiences, for general audiences, which is really where science and philosophy sit together. For example, in A Universe from Nothing, the first section of that book is really a discussion about how a scientific model of this collides or sits next to or interacts with a scientific model, with a philosophical that the philosophical and the scientific sit next to each other, and you're really answering a whole set of questions about why a scientific model is more illuminating and has greater validity.
Well, it can be tested.
Can be tested.
That's for me the big point.
And I mean, it seems to me that both of you have written a lot about these issues, and that these questions, part of the charm of these questions in science comes from the fact that they are tied to this tradition of questioning about who are we, where do we come from, why are we here, what is this world, this universe that we're sitting on. And, you're reasonably dismissive of some of the philosophical possibilities of that particular thing. But what is it about those questions? Is it the philosophical aspect that makes them appeal to you?
Well,
and Rachel, for example, is this part of the charm for you of these questions? Is that you are really, with this research, you're potentially coming to answer these big questions?
Oh, look, absolutely. I think it's one of the great privileges of why we do this. I think the only unfortunate thing is that with all the paperwork and everything else that we do, we don't do it more often. So, yeah. But yes.
And what's the big question? What's the big question for you?
Well, actually, despite the fact that I, work in cosmology, I think the issues around life in the universe are actually the fascinating questions.
Mm.
I think what, look, I make fun of philosophers, but we're all philosophers. I mean, we all do philosophy, and which is, if we're doing it right, which is asking questions and critical thinking. And so it's those, you said at the beginning, I think at the introduction, it's those universal questions. We all want to understand ourselves. That's why I called my project the Origins Project. What people need to know, and one of the reasons why I go out and talk about this stuff, is that these aren't esoteric questions that are irrelevant. If we want to understand ourselves, these are questions we have to ask. Some of them may seem very esoteric in the end, but they all illuminate us. And in that sense, and this is what's so nice to be at the Sydney Opera House in this way, to me, that's what makes science the same as music and drama. And all of them are what we, as in principle higher beings, do to illuminate, to cast a new light on ourselves. And so science is cultural. It's not technological. It's part of culture.
Paul?
We must remember that all of the current scientific problems started out in philosophy. And the classic example is atoms. Democritus postulated the existence of atoms on purely philosophical grounds, trying to understand the difference between permanence and change. And so it was just a theoretical idea for over 2,000 years. Now they're part of physics. The nature of time, that was another one that's been pondered over by philosophers and still is, but transformed by Einstein and the theory of relativity, the nature of matter, and so on and on and on. So what happens is, as science progresses, it appropriates a lot of those questions that have been asked by philosophers and often changes the way that the question gets asked, or it defines the problem away. And so one of the great areas that we agreed not to talk about, that philosophers still are preoccupied with, and science hasn't made a lot of progress on, is consciousness, mind, the mind-body problem, and all that whole set of issues, big can of worms. And as Lawrence and I were coming in, I said, well, of the three great origins problems, we have the origin of the universe, the origin of life, the origin of consciousness. The origin of the universe pretty much wrapped up. The origin of life, you see, we're hot on the trail. But the origin of consciousness, we don't even know how to frame the question properly. And so we usually agree not to talk about it. So I won't say any more.
Can I ask Rachel a question?
Of course.
Because you've also been quieter than us, which is not surprising. But you said life is the interesting question to you. And I was wondering, when you talked about your biography, I know you're supposed to answer the question.
No, go for it, Lawrence.
I was intrigued. Were you also driven to math because people tried to funnel women into biology and not into math and science? I mean, and was that attracting? Was that a reason? One of the reasons why you maybe went into it?
Look, it was part of it. The other part is I faint at the sight of blood.
Ah, okay, that'll do it. That'll do it. It's easy. Okay.
So we'll go up to microphone 3.
I've got a couple of small questions, if that's okay.
Just keep them quick.
First of all, with the gravitational waves, you said they'd prove inflation. What kind of shape or form of gravitational waves would we be looking for to prove or disprove it?
Okay, well, first of all, I didn't say they prove, but inflation produces, we think, a unique signature. I spent a lot of time trying to find other signatures that look the same, because before we say we've discovered something fundamental, we have to make sure the straw men are ruled out. But what inflation does is predict gravitational waves over a wide variety of frequencies, especially gravitational waves on scales so large that no local process after inflation could have created them. Namely, if the wavelength is larger than the size of the visible universe, then nothing I'm going to do shaking anything here is going to create such a wave. And so the characteristic of the waves from inflation is the fact that they occur on frequencies right up to the size of the whole universe, and that's one of the characters of it. And there are other fine details, but it's very important if we actually detect it that we're able to demonstrate that all the other possibilities are ruled out. The other thing is that when I shake my hands, I'm not only creating gravitational waves, I'm moving around real matter. And processes in the early universe other processes in the universe that would produce gravitational waves would also produce things like density fluctuations. And so you can look for other signatures that, if they're not there, could have only been produced by inflation at that scale. It's a little bit technical, but it's a very important question, because extraordinary claims require extraordinary evidence. And if we're going to say we've measured something from the beginning of time, we've got to make sure the other possibilities are ruled out, which is in some sense what the observers found. In this case, it was a boring answer. It was dust. Dust produces, and dust is the boon and bane of astronomy, I guess.
Some people like dust.
Yeah, some people like dust.
Careers
some people study dust. But so in this case, they discovered that this signal, I mean, it was amazing. This signal looked so close to everything we'd predicted. But it was realized that there were happily realized that there were characteristics of the signal that you could show meant it probably wasn't the answer. And I'm answering too long, but one last thing I want to say, because to me it demonstrates the importance of science. These people made this discovery, made this claim. There was this other satellite up there called the Planck satellite that basically claimed the contrary, and they wanted it to not be a discovery because they wanted to win the Nobel Prize. And these two groups were completely coming up with opposite claims. What did they do? They didn't cut each other's heads off. They decided to do a joint experiment and work together because what they wanted to find out was who was right, not what nature was really telling us, not whether one or the other was right. I think it's a beautiful, even though it's unfortunate that a claim was made that was overstressed, I think it's a beautiful episode in the history of science because we could find out that it was specious and people worked together to find that out. Mm-hmm. I gave such a long answer that maybe you don't want to...
No. And I'm sorry, we're just going to switch over here to take a question. Thank you. Microphone number 4, please.
This question is directed to Professor Krauss. It's something that Professor Webster touched upon earlier. Professor Krauss, your book, A Universe from Nothing, touches upon not only dark energy but dark matter, the empirical evidence for it, and its possible origins, but perhaps the origins are less explained within the book than the observational proof for it.
In that book, I've written another one where I talk about other stuff. Anyway, go on.
Yeah. But could it be conceivable that in terms of the origin of dark matter, of which we know very little and of which we hope CERN will illuminate, that the origins may have something to do with the quantum fluctuations in those early nanoseconds where positron and electron pairs were bubbling in and out of existence at a very young age, and they just happened to be frozen through one of those phase transitions? Well, it may be that the antiparticles themselves that were frozen in time, in density, that may be responsible for the dark matter.
Let me... the answer is no. Namely, it's not antiparticle matter. We've measured... antimatter is quite visible, and if it's not completely isolated, and we've shown that really the universe has very little antimatter. It's produced in cosmic rays. But it's a big question that we want to answer, is why is the universe made of matter, not antimatter? But what's interesting about dark matter, and I've spent a lot of my career on it, is that unlike dark energy, there are a lot of good ideas. And in fact, it would be amazing if we didn't live in a universe full of dark matter. But just think about this. The most visible thing in the universe is, in some sense, is light. The cosmic microwave background, there's 300 photons per cubic centimeter everywhere in the universe. They're cosmic microwave background photons. In fact, if you're old enough, like me, to remember TV before cable, if you unplug your cable and you look at the static, a few % of the static you're seeing on your TV is microwave background photons. So that's the most visible thing in the universe, but it wasn't discovered until 1965 by accident. Now, we know that that for every proton in the universe, there are 1 billion photons. And yet, those photons remained invisible until 1965. If there were other particles that were slightly less easy to see than light, first of all, it would be surprising if there weren't as abundant as photons. And secondly, it wouldn't be surprising at all that we haven't seen them. Almost every theory in physics beyond the Standard Model predicts dark matter. In fact, the problem is there are too many theories of dark matter, not too few. So it's a very interesting area because we're likely to know the answer pretty soon, as Rachel, I think, astutely pointed out. So, but it's not, the best candidates are not ones not coming from quantum fluctuations in the early universe in that sense. They're produced by those, just like matter, but their nature is probably elementary particle physics of the type we'll see at CERN, and they're not antiparticles because we know there aren't enough of those to make the dark matter.
We've got time just for a few more minutes of discussion, and I'm afraid I'm going to monopolise that, so my apologies to those questioners. I want to finish by asking each of our speakers to talk about something something about the context in which they're working now, because it seems to me a number of things have come up in our discussion about the age we live in, which determines the political priorities of what science is funded, what kind of experiments are funded, but also some things that are characteristic of the stage of scientific development we're at in a whole lot of other areas. And I want to start with Rachel, because it seems to me, as the observational scientist here, that the era of big data, the fact that not all of a sudden, but progressively, the amount of information that you are able to gather, what difference does that make to what you think will come out of that research, apart from the fact of having to wade, that process of having to go through so much information to find what is potentially relevant?
Oh, look, I think in the last 20 years, sort of cosmology has just gone through a revolution, right? And it's a revolution for the amount of data we've collected, the range of wavelengths that we've looked at, been able to look over. So we used to just look in the optical and the radio, and now you have satellites and maybe even gravitational waves that can see in all sorts of different regimes. And so our picture of the universe is infinitely richer than it was. But the third revolution, I think, that has been crucial is the computational revolution, because none of this we would be just completely at sea if our computers weren't, the capacity of our computers just weren't growing exponentially. If that exponential growth doesn't keep going, then we're basically going to be swamped, I would say. So it's bringing all of those things together. In terms of the questions we're allowed to ask and funded to ask, it would be wonderful if we could just follow our passions and be funded to do whatever we like. It's not quite as good as that, unfortunately. I think astronomers have captured a lot of the public interest, and so I think we do reasonably well, funding-wise. But I was saying to Paul earlier that I'm sort of surprised that the fundamental questions about life, and the sort of research that Paul, in fact, pursues, has not been pursued as vigorously as the fundamental questions about the universe. And
we'll accept more money, no problem.
So it's an interesting, blind spot, I think, in terms of what we could and should be looking at.
Can you take up that question? Because I think it was very interesting saying about what NASA will and won't fund, and what seemed to be a residual scepticism left over from the period that you talked about in the 60s, where people thought any discussion of life on other planets was crazy talk.
First, as a general point, see, Rachel's worse off than Lawrence and myself. We are theorists, so our research moves at the speed of thought. Whereas if what you're doing is building the square kilometre array, this is a decades-long project, and it requires a lot of money and a long-term commitment.
And we can be wrong most of the time, but they
that's right.
better not.
Yeah, we just move on to the next thing. But there's another important point that I'd like to make, which remember Brian Schmidt visited ASU a year or so ago, and he gave a very good lecture in which he said, and I call this the NSA model. So the National Security Agency sucks up everybody's phone call, all the data, sucks it up, not because it's interesting, but because they can do it. So they just accumulate vast amounts of data. Right, so astronomers can accumulate vast amounts of data, but Brown made the very important point that the difference is that in astronomy you have some idea of what you're looking for. It may be wrong, you may find something completely different, but you have a model. You don't just say, give us a big telescope, and when we've got it, we'll point it up there and see what we find. You have to have some sort of conceptual framework so that you know what information you want to keep, what you want to throw out. That framework is a really important point. So coming back to your question about NASA and asking the right questions, you might say, well, Mars is everybody's favorite to look for life beyond Earth. Why not just send another biological package to Mars? And there's a lot of politics involved. And so I talk to people like, for example, Chris McKay, who works for NASA, who's always proposing biological packages. He once had one flown, but by the Russians, and it ended up in the Pacific Ocean, or maybe it was the Atlantic, I don't remember.
Life there.
And of course, Britain's famous, cheap, ill-fated Beagle 2, which was going to sniff out life on Mars, and has now been discovered on the surface of Mars. And for all we know, may have sniffed it out, and its antennas pointed the wrong way, and it's saying, I found it, it's all going off to Alpha Centauri. We don't know. But, NASA won't do it, and you might say, well, what have they got against it? And as best as I can find out, it's, well, the Viking mission was very, very expensive, and what we don't want is another expensive fiasco where what we get is inconclusive answers, having spent $2 billion or something. I think that's very sad. I think they could do Gill's experiments again. He's got this idea, you fire darts, you do these left and right things, and you do it miniaturized and much more efficient. I think it should be done. I hope it will be done one day, but NASA seems implacably opposed to doing any biology on Mars.
Well, I think the point people don't realize, and I often disagree with my friend Neil deGrasse Tyson on this, but it is one thing is true, is that space exploration is not, the funding of space exploration has very little to do with science. It's mostly to do with politics. And that's an unfortunate reality of life. And so the science enters in, and it's really lucky when it gets done. But the priorities and the things that are driving it are geopolitical in other ways, and that's unfortunate. But space is expensive. But that's one of the reasons why it's a real waste of money to send people up there, because it's a lot more expensive, and you have to get them alive back and all those things. And whereas as I often say, you could send a rover to Mars for the price of making a movie about sending Bruce Willis to Mars.
Ah, that's right. That's right.
Lawrence, before we finish, as a final thought, you've notably written quite a lot about science and popular culture, and one thing that's come out today is that the stories that we tell ourselves about science and the questions that we try to answer are a really important way of framing the questions that need to be asked, but also of communicating it to other people. And you've looked at the physics of Star Trek, at all of the kind of manifestations of crazy science in popular culture. What's your favourite piece of fake science? What's the thing in that world of popular culture that you would most like to have been real?
Oh, the reason I wrote the physics of Star Trek, I guess there's an answer to that. I don't know, if I think more, I might have a better one, but I'm not going to. Is the reason I wrote the physics of Star Trek is the transporter. And if anyone who spends as much time as I do in airports going through security lines, I would love to have a transporter. And it would be great. It would be a wonderful thing. I think the idea of being able to... but unfortunately, it's the one thing that I think is most unlikely, or in fact, I would say impossible.
Well,
but,
maybe only in one of those simulated universes that we were so scathing of.
Well, that's, exactly. Well, you can send the information. It's the atoms that are the hard part. Yeah.
I want to thank you all very much for participating in our discussion this afternoon. For those of you in the audience, I want to thank you. Who were able to ask questions, I want to thank you. Thank you all very much for coming. You'll be able to catch up with this discussion online, as well as pursuing it amongst yourselves. And also, there will be a whole other version of this conversation happening in Melbourne, which will also, I'm sure, pose some interesting questions. Thank you to Paul Davies, Lawrence Krauss, and Rachel Webster. And thank you very much to all of you.